Test. Okay, there you go. And maybe so. Da, 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 da. Display capture, maybe. Oh. Display. Yeah. So. Okay. Maybe that works. So here. No. Take that one away. Take that one away. There. Nope. So lock that. Where should I put myself? Maybe up in the corner? Oh. Ah, there is good. So. Okay. Maybe I would rather do a browser game. No, media source. Window capture. That's the one. Then I can do this. Okay. Then I take away the display. I think that is better. That's cleaner. Then I can show specific windows rather than everything that is on the screen. At least for now. Ah. Da, da, da. Okay. So, basically I want to make an NFC reader. That will be the project. That will be the project. Wait. I will do maybe I'll create it here. New project. NFC reader. Let's call it tap. NFC tap. Because all I want to do with it is basically make a reader. Just tap a tag on it. And I don't know yet what it will do. Maybe just something fun. Who cares? It's not really, the point is not really to get caught up in the details. It's more about taking it from concept to production and, figure it out as you go on. So NFC tap, we'll call it maybe I'm gonna have to do screen capture after all, because this is not really working as it should, I think. Window capture, I take you away. Remove. And then do display capture. This one, capture cursor force SDR, I'm not sure what that is. Okay, but now you see at least the windows and everything. Oh, and I wanted to record, so I'm gonna press record and also record this stream. So I'm gonna make an NFC reader. That's it. That's it. I'm gonna make it as simple as I can. And I have a mirror that I can use. To just draw it up. Okay. So there you go. Okay. So basically what I want to do, I'm going to make it as simple as possible. What we need is an NFC IC, because the whole goal is just doing it the way you think it should be done. And then, of course I'll make it blue because I like blue. Yeah, this is at its core. We need an NFC IC. Now what am I doing? And then we need MCU. Okay. Guess I need to zoom in for this to be properly visible. Okay, we try that again. At its core, we need NFC IC, because that's the reader. And then we need a, like I said, learning by doing. Then we need a MCU to be able to get this information, right? Make that not that color, but I like gray. Maybe a bit lighter gray. Like, the fun thing about doing these things is to really just go with your own flow. Try to figure out how you like to work with it. Because just doing it after someone else can get tedious. Okay, this music is a bit distracting. Hip hop, maybe. What in the world? Yeah. NFC reader. Yes, Yes, and in order to power this, we need, of course, I'm just going to use like USB to power it. So we need a USB like 2.0, right? That's the normal one, I guess. Let's just write USB. Doesn't really matter. And we make that like, let's say, USB connector. That's what we need. USB connector, just to power it. We're gonna hook up the thing. It's gonna be active, and as soon as you put a tag on it, it will read. I feel like I'm putting myself a lot on the spot here, but that's the whole point too. To be able to, make a concept on the fly, which is something I really want to learn and be better at. And here we'll do a simple LDO, which will then power this one. So here, +5. And here 3 point +3 V3. Something like that. Just to give a sense of what's happening here. This should be communicating through like SPI or something. And then I really want to do, I'm not sure if it's needed in every project, because you can also, route from here like this, and let's say like data or flash or something, right? But here then you can also have a zero wire debug. So I'll make these, or this one, maybe red. Okay. Damn. Like light red, like this. Debug. We can make. You gotta take your time with this. Just kind of have fun with it. Dark gray, no. This one. So connector or testing it out, you hear me? Yeah, debug, whatever we call it that. MCU. So this is where we're at. We don't really know what this MCU is gonna do with it, but that's not the point. That is not the point right now, at least. We'll figure that out as we go. I think I want to do this instead. It might seem trivial what I'm doing, but it's really beneficial to kind of draw it up for yourself so you see what's going on. And then it will be easier for someone else also to understand. Maybe I should just write here near field communication. If anyone doesn't know what that is. Because you might not think about it, but you have one in your phone, you have one on your key cards, on your bank card, everything. Or it's a tag, I guess you would call it, and not a reader. It's more the payment terminals is a reader. You know, door terminals, or, you know, access terminals. If you want to enter buildings at your job or something, you beep your card or your chip or something. So basically what is coming out here, I'm not sure, I think maybe it's 2 signals coming out here. But we can just put it up like this. Filter, what is needed? Filter. And then we need some impedance matching. And then we need the antenna. I'll make all of these dark blue. Why not? And also bidirectional, because we're sending out. Are we broadcasting or are we sending out? I need to read up on C reader. Yeah. So NFC reader is a device such as your smartphone or a payment terminal that initiates a short-range, low-power radio communication to power up and retrieve data from a nearby NFC tag or another NFC-enabled device. It enables contactless actions like making payments, sharing information, controlling smart devices, and unlocking doors by exchanging encrypted data over a magnetic field, all within a few centimeters of distance. So I can also maybe even show it here. How it works. Initiation, the NFC reader, a power device with its own power source, generates an alternating magnetic field. When an NFC tag or another NFC-enabled device comes within this field, the reader's magnetic field powers up the tag's embedded chip through inductive coupling. Yeah, that's right, the inductive coupling. So you have the antenna, and then you put the tag, and you have coupling between those because of this magnetic field. And communication modes: reader, writer, peer-to-peer, card emulation. Yeah, and then common uses: contactless payments, information sharing, access control, device pairing, smart home automation, gaming. That's the response we get back. So and that's basically this, I think. Debug. We don't really get into the details here. Basically, all we need is a USB connector. We plug in a cable. I don't have a cable right here, I think. We plug it in from our computer or something, which is, I think it's typically 5 volts. We use a linear dropout regulator to 3.3 to power this MCU microcontroller, which has processor, memory, all that good stuff, peripherals, one of which is the SPI, and it also has this zero wire connection. Maybe I should write that zero wire debug here too. And this is like a pad thing. Oh, what was it called? What was it called now? I need to Google. Could also use JTAG, but I will just write like this: connector or connector. So, and here we have the zero wire debug. The MCU, which will have the firmware and do something based off of maybe some information from the tag. Maybe it sends a message to a website or something like that. That's, that could be an example project for the future. We have the NFC IC who supports the NFC protocol. And we will also go into detail on how that works and, what is this chip? What does it do? How does it operate, communicate, etc. We also haven't put any power over here. Just for the simple fact, I can't remember how it was. I worked with these chips before, but now I can't remember. Probably 3.3 as well. And then we have, so there's signal going out and back again. And we might need some filtering on that. Then because it's a RF design, or there will be, maybe I can write on that too. So the antenna itself needs to operate at, I think it was 13.54 megahertz, which is the operating frequency, you would say, of the NFC protocol. So in order for this antenna, so we need to design the antenna itself, or we want to do that, or at least I want to do that. I want to learn how to do it, or I know how to do it, I just want to do it. That's the whole point. Build. Great. So it will be fun. It will be really fun. So we need it to operate at this frequency. That means that we need to most likely match this antenna for it to have a resonance frequency at this frequency. So when tags, NFC tags, are placed over, it will get proper coupling and it will be able to retrieve the information and etc. etc. I don't know all the details. That's what I'm doing here. I'm learning it. But yeah, let's start here. An impedance matching, that's a yeah, basically in order to, I'm not sure if it's even a point of talking about it now, but my knowledge of impedance matching is basically when you send or you generate a signal and you want it to radiate out of this antenna, in order for all the power, all the signal, or to get all the power and the signal out of this antenna, you need to match it properly. And if you don't do that, you get reflections, meaning that you don't get that 100% out of the antenna, but you might get reflections backwards again, and therefore, yeah, not getting out all the information perhaps, or maybe it doesn't work as efficient, or it doesn't work properly. Yeah, this is all something to learn along as we go. So in the future, we'll be able to talk about it like we know what we're talking about. Because I feel like I know what I'm talking about up until some point. But I'm not going to stand here and pretend like I know everything. So, but generally this is what we have, right? So antenna, NFC, IC, all of these filter and impedance matching, making sure that the antenna and the signals are what they should be. And then we give that information to the MCU, the microcontroller, and it does something. That's the project. That is the project. Oops. This is what I was fearing. Okay. Just give me one moment. Live control panel. Let's go into KiCad. So for the sake of just, going along and not stop up too much, I'm gonna be using the symbols and footprints already available to me. And I think there is an NFC chip called EN something. NFC field communication controller. Yeah. NFC front end 5120. I mean, I could just write in NFC, right? See what I get. MCU NXP end. Oh, this is a, okay, so this is a tag IC. Interesting. Then you have this one. Oh, that's RFID. That would be a cool project to also try. I would like to do that. But maybe this one. Let me just Google real quick what this one is all about. The PN532 is a highly integrated transceiver module for contactless communication at 13.56. I think I wrote 54 before megahertz, based on the ADC51 microcontroller core. It supports 6 different operating modes, so it can be a ISO 14443A, MyFair Reader Writer. Okay, so it's A, B, Reader Writer, Felica. I worked with this before, so I recognize these ISO standards. This MyFair card, what was that? Emulation mode, card emulation, and here's the peer-to-peer. But I guess this one is maybe the one we focus on the most, Type A NFC. We can maybe Google this one as well. Reader writer is a device. Reader writer is a device that can both read data from and write data to contactless smart cards that adhere to the ISO IEC 14443 standard, particularly the A variant, MyFair cards. Yeah, cool. Just skimming through a little bit, so it has a SPI, so let's use that, or I squared C. Allows the device to be connected directly to a battery, and additional power switch is included to supply power to a secure IC. Oh, right. Allows the device to be connected directly to a battery. So this one actually has a MCU or microcontroller in it. This one. Wait, well, 8-bit microcontroller. NFC, PN, 5. Okay, maybe we look at something different. Another type. This one maybe it was. this one, maybe. And this one is not recommended for new designs. We recommend using PN7160. So look at some antenna interface. Here's the antenna interface too, so you can look at how it should be connected and roughly how it should be designed. And here is also an antenna design guide. Smith chart. Okay. Okay, so let's just say we can go back to this one and we write it on here. That this one is the one we would like to use. And since I also like working with the STM32, I will use that here. EN7160 and 7160, which is not here. '56, right? 56. Yep, learn by doing. Okay. So we're gonna have to make, we need to go back here. Need to go back to the symbol editor and just make a symbol. No symbol library. Okay. Put it here. The symbol name PN7160. U1 and we need now I need to put up the data sheet on the other side. Data sheet. We got a lot of like resources, which is good, I guess. You have different types of like RF settings guide, configuration files, frequently asked questions. hardware design guide, which is good, obviously. Yeah, so you have one BGA package, ball grid array, and then you have a HVQ flat something, quad flat 40. So with like a exposed pad or a thermal pad, and then 40 pins. There's the SPI, I2C, VDD, ground, enable. And how they should be connected roughly. Should be left open. Yeah, that's on the BGA. So you probably have like some connected to ground and then some open, etc., etc. Cool. Very cool. So here a little bit of the functional description. So you have the NFC C, and then antenna matching, and then the antenna. Here's the host interface, so like SPI, which we roughly already decided that we will use, to the application processor. Then there are external supplies and clock. Right. So here's the polling phase. Emulation, then it does type A's. If there's nothing there, it checks for type B, then type F at 424, at 212, and then for this particular variant, interesting. And that is what is this? That's a listening phase, and then the polling phase, I guess. A listening phase, and then polling phase. And I worked with this before, so it's fun to see it again like this. You know, I was testing and creating test cases and such, and I would look at how the protocol and how it was working with like sniffers and stuff to see how it goes through this polling phase and checks for type A, type B, etc. Interesting. A crystal, 27.12 megahertz. And a battery can be plugged in directly, I guess. External 5 volt. Oh, right. Yeah. If there's a battery, it can be supplied by that one or from an external 5 volts. So, for example, a USB connection or USB power supply, you would say. Resetting PN7160, reset and download concept. Okay. And there's so much information here, right? But that's not really battery supply. It needs to be, if it's a reader, between 2.8 and 5.5 volts. BDD pad supply voltage 3.3. Was it 2? Oh. Battery supply current. Okay. There was a current limit threshold 2, current limiter on transmitter. Yeah, like I said, we don't have to go into the details really until we would have it produced, right? And maybe do some testing with it too. Okay, let's skip ahead. Okay, so this is what we will do later then. If I haven't already created a footprint like this, but we can go back here and we can create the same footprint. Or download it, but I want to make a point out of doing it yourself. You know, I feel like that's the whole point of this, is to kind of, even if it theoretically is possible to just download it and it will save you a lot of time, yada yada. Right, I will put this here and see if I can find like a nice picture of all the pins. Hi Twinkie Pie. Hiya, hiya. Okay, bye bye. Thank you for stopping by. I'm just having some fun. Just stopping by, yes. I'm just working. Learning as I go. Right. Datasheet. Hardware design. Yeah, okay. Here we got it. Here we got it. I can zoom in. Yeah, I mean, that works. Right, so this is the package that we want to use. And maybe I'll just Google what this package is. HVQFN40. So the HV stands for highly thermal enhanced or thermally enhanced. So the HV, thermally enhanced. While QFN signifies quad flat no leads package. And that makes sense. Because if we go to, okay, this is the same, okay. We go to the same one here, thermally enhanced because it has this VSS or ground thermal pad where we can put VS down to a ground layer and dissipate the heat. So HV, high V. How can you connect that so you remember it better? HV, high V. Highly thermal enhanced or thermally enhanced. Yeah. Maybe not so easy to remember, but quad FN, quad flat no LEDs package. So it's a quad package, basically, right? And flat no LEDs, so no. And then of course the 40, which indicates the number of pins. So quad flat no LEDs. So no LEDs means so the no LEDs portion of the description means the package does not have traditionally protruding LEDs, but instead has flat contacts on the bottom. Of course, and very nicely put. So it doesn't have, like, for example, SOT23 package, for example, like this one, which is maybe more common for like a BJT or something, like a transistor. Yeah, like this small outline transistor. Damn, it's even called that. I didn't think about that. SLT, small outline transistor. Here it has these LEDs sticking out and taking up space on the PCB, right? But here is a no quad, no LEDs 40 pin. Highly thermally enhanced. Okay. Let's not even go into the BGA. We focus on this and we find a nice picture. So I will use this and I will create a symbol for our component. And then I would like a list of all the pins. If I can find it in a bit better quality, because this is not so good quality. Hold on. Okay. So I have the picture. Yeah, and then we can use this one, right? Pin 1. And then we go down and put it up. There you can even see what type it is and what the pin name is. Like C3. Oh no, sorry, that's the BGA. 1, 2, 3, 4. And the reference, I guess. For yeah. If you see something I don't see, please let me know in the comments. Good God. Let's speed it up. Or we won't speed it up, but see if I can take this on the side here. Number 1. And guess it's an input. Oh no, wait. Oh. E, yeah. Alternate pin name. Can I just continue? No, I will just do it like this. A little bit manual work, but that's alright. We'll get better as we go. So we have the first one. We can take away that one. And then basically we continue. And I will put the other this one's on the other side, so it goes a little bit quicker. And I think the other one could be bi-directional. Anyways, this is at least an input, so we'll put that on. So, and actually what we can do is we can just put on these names. We don't have to include both I2C and the SPI, because they can both be configured to use that. But since we want to use the SPI, okay. This 2. Okay, this song is a bit scary. Hold on, I will turn on the music here. Okay, so we just have a bit music in the background. Add 4. Oops. VSS add pad. This is 4. This is electrical type, power, input, you would say. In KiCad symbol creation, both VSS and ground pins are typically defined as power inputs, as they are the points where a component receives power from the system. Symbol definition of its component's requirement for a ground connection, not its ability to supply it. So it's a power input when you are making pins that are either a ground connection or VSS. VSS and ground pins. Okay. Next one. And this, we have to do this 40 times. SPI, ISO, master in, slave out. 5. And this, and then master in. But you specify that as a bidirectional then? Whatever. Next one, VDD pad. In number 6. So this is then a power input. And then we got the clock, SPI clock 7. I would call that an input. Interrupt request, output, pin 8. VSS analog in number 9. So then that is also a power input, right? There's a ground connection for the analog part. Yes, put that here. Could actually already kind of move them where they should go. So, you know, you would put the SPI pins together at one place. You'll put the power at the top, the SPI, and then maybe the ground at the bottom, and then the rest of the, you know, receiver or transmitter inputs and outputs on the other side or something. This is the part of like schematic design that I really enjoy, where you're really making, you're putting the effort into making the schematic as nice and understandable as humanly possible. You want the schematic to look good, so you yourself can look at it and understand what's going on. It's not technically a power input, is it? Rather say an input. Then this is the reset pin, set the device in hard power down. Okay. And then we have internally connected to be left open. Oops. I wonder if it's best practice to name them like this, or if you should have it like this, like not connected like that. I can do it like it is in the data sheet for now. I'm not sure if it should be like that. At least it should be more intuitive. Like do not connect or something. 11, pin 11. V BAT2. This is then power input, and it's pin number 12. VDD up 13, also power input. This is the transmitter LDO input supply voltage, or TX LDO input supply voltage. Not 100% sure what that is, but we will get there. And then the VDD TX transmitter supply voltage 14, power soon halfway, or XN, so negative receiver input 15, do like this, input, RXB 16, input, the positive receiver input, VDD, mid, reference, receiver reference input supply voltage 17. This is a power input, so power input, TVD, TVDD in, must be connected to VDD TX and TVDD underscore into. Okay. 18. This is also power input. So TX2, 19. Antenna driver output. Where is it? VSS TX, so this is a ground. So it should be a power output, no input. What is this psychedelic, crazy psychedelic music? Okay. So that's the contactless transmitter ground, must be connected to ground. The VSS or VSS TX. And then we're at TX1, 21. This is antenna driver output, so it's an output. TVD underscore into 22. This is a power input. Antenna 1, pin number 23. And this is then antenna connection for wake up. Says that is power input. Okay. I mean, all of these electrical types, it just helps during like when you're doing electrical checks that you know, if you route something that is has a property that says it's an input and it's connected to another input, it might give you some warnings or maybe even errors saying you got two input ports or something. So, but as long as we understand what's going on, everything will be all right. And this is antenna 2, antenna connection for wake up 2 and 2. Also the same. Monitor rectifier output voltage. Or output, maybe. I'll put it as a power input, but we will go through this later on anyways. VDD HF, and then we're at VDD analog, so the power input for the analog supply, 26. Then we're at VBAT, so power input. No, wait. We're not at VBAT yet, VDD. $27. And then VBAT 28 was a power input. X-tau2 oscillator output. So 29. And we'll call it output. Why did OSB disconnect? Okay. Yes, X-tau2, which is an output, oscillator output, and then we got the NFC clock X-tau1, PLL, phase lock loop input. $30. Input. Oh, wait. No. So VDD, digital supply voltage for decoupling must be connected to VDD and VDD-A. 31. It's then a power input. The power input. And then we have right. Then we have some pin names that should be not connected. 32. How to place pins? Wait, let's test this. We'll take this, and then we do like that, and then we no. Oh, maybe I need to put in preferences, symbol editor. Hmm. What do you press? Right. 34. Maybe this we put 3 unspecified, unconnected. Mm-hmm. Do, 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 do. Do, do, do. 36, last unconnected. Yeah. Where's the 34 here? 34, 35, 36. I don't know what was simpler. Maybe just continue doing it like this. DC enable 37. It's apparently an output. Then an internally connected to be left open. Free unspecified. Maybe like this. Wake up request 39. This is an input. Clock request 40. And then we have the VSS, which is, it doesn't really have a number, right? And then another one that's just internally connected. Oh no, that's not on this package. That is on the BGA package. So this is the center pad. VSS pin number. I can do it like this: center pad. Why not? So that's all the pins. That's 40 pins. That's a thermally enhanced quad flat no LEDs 40. Okay. So now we're making the symbol. We're making the symbol for this component. And we can just make something like this, right? And then we give it a color. Let's for fun try and follow the same type of oh no, that was the border. I don't need the border. I would like to do something like this, maybe. Fill with body. Color. Okay. So, a bit grayish. Or actually, I'd made it blue, didn't I? So put it here and put on the opacity to 20. Something like that. And then we can basically place them around where we think they should go. And for example, I'll select every VDD first. Like all of these. And I'm not sure if all of them should be connected, right? But you see it's all power inputs as well. So might as well. Can I align them? Align. That's in the PCB editor. Oh well. And then I will take, so here we have all the power pins. And we got the SPI stuff. Oh, come on now. There, and then VSS. That's the ground connections. This power input can go here too. Here is this. Put them here. Wish you could like put them together, kind of. Let's do it manually. Should also be a power input. And then, for example, the xtal2, xtal1. Oscillator input and output. The not connected can go somewhere here. The internally connected, they were also supposed to be left open. DC-DC enable. Wake up request. Clock requests. Okay, we need to start placing this out. I will start with putting these up here. Okay, that doesn't work. What the hell is going on? So we'll put this a bit up here maybe. And then we'll align the first pin on this one. And then we give like one box up. I like giving myself a little bit of space at least to place out the pins. And now what I can do is I can use the datasheet as a bit reference. And for example, this is, I don't like how it's set up here, right? This, I mean, on this one, for example, here the power interface is at the bottom. You have some VDD pins here as well. And then when you have ground here you have something. And then VDD here as well on the right side. Antenna interface. I don't know what this was again. This is the antenna interface. The clock at the top. Host an interface like SPI or I2C. Then host GPIOs. So the interrupt request, the enable, the wake up request. So I could use it as a reference to not, or to see what not to do, maybe, or to kind of do the opposite. But I wish I could. No. Let's do that one then. And then we put all our power stuff at the top. So I don't know. Doesn't really have to be in any specific way, I think. You see here is pin 6, 27, 26, 25. Yeah, we can start with this and then kind of just go down. And I think this makes a lot of sense to do it this way. VDD up, TX. We can tweak this how we like later as well. First off, we just do it. 17. Okay. 17, 18. TVD. What is all this? Wait. I need to check the data sheet. Da-da-da-da. So basically what I'm trying to figure out is how this thing is supposed to be routed, right? So common thing to do is just to look at a data sheet, or in this case it's a application note, hardware design guide, and you can keep looking at the BGA package and you look at this component, right? Look at the power interface. So I like to have those at the top. Makes more sense to me. You see how you power the thing, and then you see maybe coming, the signals coming to it, and then the signals leaving it on the right side, the ground at the bottom, and then, other types of signals here and there based on where they're going. If they're going to the host, like here, the clock, yeah, just where it's logical and where you can make a nice schematic design without it being too hard to read or something. So VBAD, VBAD, VDD up, VDD pad, and down here, AVDD, VDD, and DVDD. This is not okay. Then here the ground. Then you kind of have to, for example, it's kind of based a little bit. We can place it here now, but it could be that more logically it should be on the top if we're powering the thing from a battery, and these pins can be connected to that again or something. You just have to look into it. So might seem like a lot of mess, but when you work on it yourself, you kind of just have to go with the flow as much as you can. I think all of these should be in the vicinity of each other at least. And then here is the digital one. Maybe these should be together like this. Something like that. Yeah, you really got to think on it if you're doing it yourself. So VDD pad. Where's that? VDD pad. It's here. It's together with VDD up and VBAT and VBAT2. And then AVDD and VDD and DVDD is together. And then VDD TX TVD in. So up and pad. Six, 13, 28 and 12 together. 28, 27 and 31. Where is that? That's 26, 26, 27 and 31 together. And then TVD in, TVD in, TVD in 2, and VDD TX together. And it could be also that they are put up like that to show how it's, this is how it's logically connected, but then physically on the PCB how it should be connected. So maybe these pins are where they're located kind of, or close to each other, since they're all kind of hooked up to sometimes the same net. Who do you think you are? Doodle-doo-doo. Ba-da-ma-ma. Okay, and then I have these two, which I don't know why. Maybe they're not. So 25 and 17, VDD V mid and VDD HF. Okay, 17 on its own, 25, 25. Just put it here. This one on the other side, maybe. Oops. Just here for now. Okay, and then we have the RXB, RXN, TX1, TX2. This is for the antenna. So this we can then put in on the other side. So 16 and 21 together. Oops, wrong side. So 15, 19, and 15. These I can also, put on the ground here. Same with the ground pins. Antenna 1 and 2 and V. Like these are not connected on the reference schematic. So I'll have to see if these needs to be connected to something or if they can just be left floating. So, so we have an interrupt request, a enable of some sort, wake up request and a clock request. I put those together as well. It says host GPIOs, so they're going towards the microcontroller then. Them here. Now we can take the SPI. DVL request. Could put a clock on this side maybe. At least for now. DC-DC enable. This I will also just put with this since it's left floating. And it says it's an output. I'm not sure what it does. So I'll just leave it. And then this was actually down together with the wake up request. Also not sure what it's used for. So, and then here we have the designator. The first pin on this line, and then something like that. This we can still have at the bottom, I think, but I was thinking maybe have the clock also on this side. Maybe we need to space things out a bit. Give things some more room here and there. And this. That's a good start. Okay, and that's 2 hours of streaming it and working with it, and we're actually done with this part, so we can go ahead and place this component. Save it. We go back to the schematic, go in our transceiver, and we put it here. Now we can, these are already not, connected. Not sure if you need to do this. Could be that you don't have to. But all of these are at least connected to ground. Oh, okay. I messed this one up. Wait. So, then I can go here and update the symbol. Yes. So, now it's aligned to the grid as well. This I can make nicer though, to be fair. But that's the beginning of this project, episode 1. So I'll basically make a NFC reader. I'll use this NFC. So another thing I can do in the schematic is actually to show which component it is. Here. So which footprint, which data sheet, manufacturer number, manufacturer part number. It was the PN7160 something something. Manufacturer NXP. And you can show it too. So. something like that. Could take away the NXP. So yeah. But this was first episode of just me doing my own thing, building, learning how to do it. And as you can see, making mistakes along the way. Which is a bit fun though. The only way to get better at something is to actually work with it and make some mistakes. So, and it's like these things you kind of forget a little bit when you don't do it all the time. But yeah, so now we need to go back to the Miro board. We have made a symbol for this component. We need to hook it up. And you know, sometimes you start wherever you feel like starting, and we felt like starting with this component, and that's all right. You take it a little bit as it goes. Sometimes it's very easy for you to maybe say how you're gonna power something. Other times you need maybe, you know, like a barrel jack or a plug or something to power something from a like a table power supply or something. But now we're just using a USB connector. To an LDO, to a microcontroller, also power to this NFC. And that could also be directly from the plus 5 volt maybe. We'll see. So it could go like this, right? Maybe. But this is cool, I like it. It's fun to just do something that you know you're gonna be working with in the future. Okay, but that's it for this episode. I have recorded it. It's almost 2 hours long. And we'll see what the end product will be. So bear with me. And yeah, let's see. Okay, that's it for today.